Good day. Today we are going to discuss about periodic motion. So what is periodic motion? Periodic motion is when a vibration or oscillation repeats itself over and over. The motion is said to be periodic. Here are the examples of periodic motion. The motion of any planet around the sun, the motion of moon around the earth, the motion of the hand of the clock, and the motion of the pendulum clock. Simple harmonic motion, or SHM, is a special type of periodic motion, which means repetitive movement back and forth through an equilibrium or central position so that the maximum displacement on one side of this position is equal to the maximum displacement on the other side. The time interval of each complete vibration is the same. The force responsible for the motion is always directed toward the equilibrium position and is directly proportional to the distance from it. Computing the simple harmonic motion, we hover the formula F is equal to negative kx, where F is the force, x is the displacement, and k is the constant. And this relation is called the Hooke's law. Here are the examples of simple harmonic motion. An acrobat swinging on the trapeze, and a child on a playing swing. Here are the sample problem. Question: how much force is needed to pull a spring with a spring constant of 20 Newton per meter, a distance of 25 centimeter, shown in the figure? The K of the spring, the K or the constant of the spring is 20 Newton per meter, and X or the displacement is 25 centimeter. Using the Hooke's formula, F is equal to negative kx. In this formula, we hover the positive constant because negative means a resting force. When pulling or pushing in the opposite direction of the displacement, it becomes positive. Before substituting the value of the displacement and the constant, we need to convert the displacement cm to meter. F is equal to K times X, or the 20 Newton per meter times 0.25 meter. So the value of F, or the force, is equal to 5 Newton. A force of 5 Newton is needed to pull this spring. Distance is 25 cm. Under the simple harmonic motion, we hover the spring mass system, which means both vertical and horizontal spring mass without friction oscillate identically around an equilibrium position if their masses and the spring are the same. However, for the vertical spring, we need to remember that gravity stretches or compresses the spring beyond its natural length to the equilibrium position. After we find the displaced position, we can set that as y is equal to 0 and treat that vertical spring just as we would a horizontal spring. Here are the important parameters to consider. Period, or the T, the time needed to complete one cycle. The unit is second. Here are the formula. T sub s is equal to 2 pi the square root of m over k, where T sub s is the period of the spring, m is the mass. The displacement x is how far the mass is from the equilibrium point. Amplitude A, the distance from the equilibrium point to the maximum displacement. Next is the simple pendulum. It is which can be considered to be a point mass suspended from a string or rod of negligible mass. It is a resonant system with a single resonant frequency. For a small amplitude, the period of such a pendulum can be approximated by T is equal to 2 pi square root of L over G. For the pendulum length, L is equal to cm converted to meter. For the acceleration due to gravity, G is equal to meter per second square. The pendulum period is T is equal to second. Example problem: a second's pendulum has a half period of 1 second. It takes 1 second for it to go tick and another seconds for it to come back tock. Questions: A. What is the length of the second pendulum at a place where gravity equals the standard value of 9.80665 meter per second square. Here are the solution. From the equation t is equal to 2 pi square root of L over G, make the length the subject. L is equal to G t square over 4 pi square. Here are the given. G is equal to 9.80665 meter per second square. T is equal to 2 seconds. Here are the solution. L is equal to G t square over 4 pi square. Substitute the value 9.80665 meter per second square times 2s quantity square over 4 pi square. Now we get the value of L, which 0.993621386 meter. Second question. What is the period of this same pendulum if it is moved to a location near the equator where gravity equals 9.7 meter per second square? How much time does the pendulum lose or gain? Solution. Back to the equation, t is equal to 2 pi square root of L over G. Here are the given. L is equal to 0.9936211386 meter and gravity is equal to 9.78 meter per second square. Here are the solution. T is equal to 2 pi square root of L over G. 2 pi square root of 0.9936211386 meter over 9.78 meter per second square. So the value of t is equal to 2.002723096 seconds.
So let's move on to physical pendulum. It is on any object whose oscillations are similar to those of the simple pendulum but cannot be modeled as a point mass on a string, and mass distribution must be included into the equation of motion. Compared to the simple pendulum, the force of gravity acts on the center of the pendulum bob in the physical. The force of gravity acts on the center of mass, or cm, of an object. The object oscillates about a point zero. The minus sign on the component of the weight that provides the restoring force is present because the force acts in the opposite direction of the increasing angle. When a physical pendulum is hanging from a point but is free to rotate, it rotates because of the torque applied at the cm, produced by the component of the object's weight that acts tangent to the motion of the cm. Taking the counterclockwise direction to be positive, the component of the gravitational force that acts tangent to the motion is mj sine theta. The minus sign is the result of the restoring force acting in the opposite direction of the increasing angle. Recall that the torque is equal to T is equal to R times force. The magnitude of the torque is equal to the length of the radius arm times the tangential component of the force applied. The absolute value of T is equal to R times force sine theta. Here, the length of the radius arm is the distance between the point of rotation and the cm. To analyze the motion, start with the net torque. Like the simple pendulum, consider only small angles so that sine theta is equal to theta. Recall from fixed axis rotation and rotation that the net torque is equal to the moment of inertia, as you can see in the formula, times the angular acceleration, where a is the acceleration. And the formula for the acceleration is equal to d squared times theta over d times squared. Once again, the equation says that the second time derivative of the position in the case that the angle equals minus a constant times the position. The solution is shown on the formula, where theta is the maximum angular displacement. The angular frequency is shown below. The period is therefore t is equal to 2 pi the square root of I, or inertia, over mjl.